Hello, everybody. We're going to start chapter 7, which is all about alkyl halides or haloalkanes, however you want to call them, and the reactions that they undergo, which basically is substitution reactions and elimination reactions. We're going to learn that substitution reactions can undergo two different types of mechanisms. There's the SN2 mechanism and the SN1 mechanism. And those two mechanisms are competing for the most part, and they actually can be distinguished based on how the mechanisms occur. And we're going to learn how I can look at a substrate, which is the reactant, the haloalkane reactant, and the conditions, including the type of nucleophile that's going to be reacting, and determine whether this reaction is going to undergo SN1 or SN2 mechanisms. I can also do that for elimination. Elimination is another type of reaction that haloalkanes and also alcohols under the presence of acid can undergo. All I need is a leaving group, and then I can have some base come in, pick off a proton, and kick out the leaving group. And then I go from the alkyl halide or alcohol to an alkene. So it's sort of the reverse of the reactions in chapter 5. There are two mechanisms for that type of reaction, that beta elimination reaction. There's E1 and E2. They also can be, they're competing mechanisms, and we're going to be able to look at the substrate, which is the haloalkane or the alcohol, and the nucleophile or the base in that case. And then we're going to look at the conditions and be able to analyze, does this undergo E1 or E2? And then there's a further compounding factor. Substitution competes with elimination. So we are going to be able to look at a substrate and look at the conditions, and not only now determine whether it undergoes substitution or elimination. That's our first level of analysis. Then if it undergoes substitution, does it undergo SN1 or SN2 in terms of the mechanism? And if it undergoes elimination, is the mechanism it reacts with E1 or E2? So this chapter is relatively short. There's only 52 slides. But once we go over these topics, the key for you this week is to really focus on problems. So there are multiple activities in the lecture materials for this section, and I really encourage you to go through them all in order to understand what types of problems that you'll be engaging with on the next test that we have. And even though we cover the material, I'd say relatively quickly lecture-wise, you do want to make sure that I will be posting additional practice problems. I'll probably also be doing videos of me doing practice problems, because this is a rather hard chapter and people tend to struggle with it in in-person classes. And what we're going to do in this module online is to try and really make you guys understand what's happening and why it's happening in terms of these types of reactions. In the first part of chapter 7, we're going to look at just the nature of haloalkanes or alkyl halides. We're going to look at the characteristics of alkyl halides, and then we're going to look at how we name them, similar to all the other functional groups that we'll be doing in the future. So without further ado, I am going to share my iPad screen, and we will get started with learning first about haloalkanes as a functional group. Okay, so haloalkanes or alkyl halides. You will see both of those terms referring to the same types of compounds. And remember, my halogens, right? Halo means halogens. So I'm looking at fluorine, chlorine, bromine, and iodine for the most part. And then remember, in this section, we're really going to focus on chlorine, bromine, and iodine. As I mentioned before, fluorine is a very small row 2 element, and it actually doesn't participate as much in these organic chemistry reactions as maybe you have noticed. So let's start with the structure of a haloalkane or an alkyl halide. Think about the fact that it has the word alkane or alkyl. So this is a compound that contains a halogen atom covalently bonded to an sp3 hybridized carbon. So remember, this is that tetrahedral carbon that has 4 single bonds. One of them is going to be the halogen, which has those 3 lone pairs around it. So this R symbol is just that generic symbol for an alkyl group. And then my X, as we're going to notice, is going to be chlorine, bromine, and iodine for the most part in this chapter. And we're going to talk about why that is. They have some chemistry that fluorine doesn't have because of their position on the periodic table. So this is the structure. Typically, these are fairly electronegative atoms, right? This one is the most electronegative, and this is the least electronegative. But I do have this sort of pulling, right? I have this carbon halogen bond, which is polar. So I get this partial positive on the carbon and the partial negative on the halogen. Now, we know that when I have a partial positive, this is an electrophilic carbon. And we're going to find out that our halogens are going to be really good leaving groups, which we're going to talk about a lot more. But initially, right, it's all about the fact that this is a polar bond. So I do have my partial positive on the carbon and my partially negative charge on the halogen. So let's talk about naming them. As always, the first thing I have to do is locate the parent alkane, that longest continuously connected carbon chain, right? I'm gonna, this again, these nomenclature rules are building. We had nomenclature rules for alkanes and alkenes and alkynes, and all of those rules that we talked about are being expanded upon. So now we're going to include our halogen atoms, our alkyl halides, to these rules. So we're just going to expand upon them. Remember, I'm going to number the parent chain, and to give the substituent that is encountered first the lower number. I'm going to show halogen substituents by prefixes. It's going to be fluoro, chloro, bromo, and iodo. And they're just another substituent. So when I have other substituents contained in the same molecule, these prefixes that indicate the halogens are going to be listed in alphabetical order with other substituents. I'm going to put the location, which is that locant, dash the prefix, so that I can give the alkyl halide the full IUPAC name. So I am going to set that location in the halogen on the parent chain. So let's look at some examples here. Here is my longest carbon chain. And if I count this way, my first substituent is encountered on number 2. If I count the other way, it's not encountered until number 3. So this is going to be On my 2 carbon, I have a methyl group. On my 3 carbon, I have a bromo group. And it is a 5 carbon chain, so it's going to be a pentane derivative. Now, I have 2 methyl and I have 3 bromo. The B comes before the M in my alphabetical order. So the full name for this is going to be 3-bromo-2-methyl pentane. Notice in this example, I have a cyclohexene derivative. So I have my double bond. Remember, I'm going to, by default, have the first 2 carbons in my cyclic alkene be number 1 and 2, but I can go either upwards where I'm showing what's, kind of clockwise, or I can sort of go counterclockwise with the naming. If I go in the direction that's indicated, my bromine gets ends up on carbon number 4. If I go the other direction, 1, 2, 3, 4, 5, I have a higher number for bromine. So I'm going to make this carbon number 1 and this carbon number 2. Notice I don't have to add the 1, right? There's no 1 because I know by the nomenclature rules that the double bond is 1 and 2. And then I can just go ahead and count and put the location of the bromo as a 4, and then add the prefix bromo that indicate I have a bromide. Right, so this is my bromo substituent. Notice that in my third example, I have a cyclohexane, but I have an alcohol. The alcohol is pretty high in priority, as we will see. So my root here is not cyclohexanol. I mean, it's not cyclohexane. My root, my parent, is going to be cyclohexanol. And my OH is always on carbon number 1. So this is going to be carbon 1, and my parent is going to be cyclohexanol. My halogen is on carbon number 2, and this is going to be a chloro, right? This is giving me the cyclohexanol parent. Now, I can do, you should notice that there is stereochemistry indicated here. The hydrogen or the hydroxy is hashed backwards and the chloro is bold hashed forwards. So there's 2 different ways I can name it. This is naming the specific enantiomer shown. Oops. So if I assign configurations to the 2 chiral centers here, as drawn on the piece of paper, what I'm going to get is this hydroxy is going to be an S configuration, and the chloro is going to be also an S configuration. Notice I have to indicate the carbon of the substituent and the stereochemistry of that substituent, that particular, the way it's drawn. So this is actually giving me a specific enantiomer. So the other enantiomer of that compound would be if my OH is bolded and my Cl is hashed. And that would be the 1R, 2R, 2 cyclohexanol, 2-chloro cyclohexanol. So notice that first naming system is referring to a specific enantiomer. The one down here, the trans, this is going to be relative stereochemistry. Oops, I always keep doing that, don't I? Chemistry, can't get too close to the end. So this would be the fact that those two substituents, the OH and the chloride, are on opposite sides of the rings, which means they're trans. Now, it doesn't give me the enantiomer, it just gives me the fact that those are trans to each other, right? So I could also have, that sort of indicates a racemic mixture. Basically what I have is a mixture of this enantiomer and this enantiomer. If I just indicate the trans, it's sort of implying that I don't have one specific enantiomer, but that I have a combination of the two. And remember, if I wanted to draw cis, I would have both of them bolded, or I would have both of them hashed. And if I was going to indicate this being cis, again, that implies that 1-to-1 ratio of enantiomers. And if I implied one specific isomer, let's say I just wanted to look at the stereochemistry here, that would be 1R, 2S, right? This would be R and this would be S. And then the enantiomer of that would be SR. And I could draw this out, except now I would have the cis and I'd have the 1 something, 2 something, depending on the specific enantiomer. So when you encounter something like this on a test, you have to choose one if it's not telling you. If it tells you what is the relative stereochemistry, you're going to say cis or trans. If it tells you what is this specific enantiomer, and it indicates that those stereocenters are specifically referring to the hashback and the bolded forward, then you need to assign the stereochemistry configuration, S or R, and then incorporate that as part of your name. So notice I have parentheses around that piece. So if there's more than one stereocenter, I need the location of the carbon that I'm referring to, and you put those in numerical order. And then I also need the configuration, which is S or R, as a sign for the particular stereoisomer that I'm referring to. So it says here, for each of these examples, convince yourself that they are numbered in the most appropriate way. This is my longest carbon chain. I could do it this way, but it doesn't matter. So my substituent is on the 2 carbon of the propane chain, regardless of which way I look at it. Here, I could number that way, but then my methyl and my bromo would be on the 4 carbon. I always go with the lowest number for that first encountered substituent. So I have to number in that direction in order to do that. And then here, I have stereochemistry indicated here, right? If I were to go ahead and number in the other direction, that stereocenter would be on carbon 3, but I'm encountering this methyl group on carbon 2 in the other direction. So that's the way I number to give the first encountered substituent, which would be this methyl group, the lowest number. Now, because this is indicated as bold, that is referring to a specific stereoisomer. So what I have to do is assign configuration. So I would have 1, 2, 3. I'm going clockwise, which is where I get the R. Now I don't have to put 5R because that's the only stereocenter in the molecule. So that R is implying that what I have is on the stereochemical center that's indicated, the configuration is R. Notice I have bromo come before methyl, and remember that's not counted in alphabetical order. So this is not counted in alphabetical order because it's tri. So or di-tri-tetra, those aren't counted. And the only thing that is counted, remember tert, sec, butyl, all of those are not counted. The only one that's counted is iso. So just when you feel comfortable with this, recognize that alkyl halides, when they're simple molecules, are also widely recognized by their common names. So the common name is where the alkyl group is named as the substituent and the halide is treated as the parent. So if I look at this molecule, which I have CH2, CH3, right, here's my halogen, which is a chloro, and then I have that 2-carbon parent. So this would be called chloroethane. I don't need a number because both of those carbons are equivalent. But this is also known, right, the CH3, CH2 substituent is also known as an ethyl group. So this is very often called ethyl chloride. In fact, in most cases, it's called ethyl chloride, and it's not really called chloroethane. So you do have to be cognizant of the fact that there are going to be times when I am using these common names, and those common names are actually very prevalent in the field. This is a dihaloalkane, right? So that's a 1-carbon methane carbon chain, and I have 2 chlorines, dichloromethane, right? So that's the IUPAC systematic name. Most of the time, it's actually called methylene chloride. So we know that this is a methyl. This is called a methylene group. And then this is called a methyne. So I will be referring, that methylene carbon is the one that's doing this. This has a methyne proton in it. So this is sort of like the secondary and the tertiary indications of a specifically proton. So it's the methylene hydrogen. It's the methyne hydrogen. You'll see that a lot in spectroscopy, which we're not doing in this class, but just so you know some of this terminology. But this is used all the time. Methylene chloride, you need to add some methylene chloride to that. Methylene chloride is the solvent. So you do need to know some of these common names because they are used very prevalently in the practice of organic chemistry. Now, there are several multiple haloalkanes that are common solvents. And again, they're typically always referred to this common, or sometimes they're called trivial names. We just talked about methylene chloride. This guy, trichloromethane, is actually known as chloroform. Probably everyone has actually heard about chloroform. That's that knockout. You know, you can soak a rag in it. You know, it's in crime shows and crime books and that kind of stuff. It does give you a nasty headache when you work with chloroform in the lab as a solvent, not so you want to knock out your coworkers or anything. You do want to make sure that you're working in the hood in a well-ventilated space, because if you do build up some concentration of chloroform, you could actually get woozy or even pass out, which is never a good thing in a lab setting. So just saying that that does have that property. And this is probably the most common ones you're going to encounter This is methylchloroform. It's because I have this CH3 group that's replacing that hydrogen. And then this is called tetrachloroethene or tetrachloroethylene. These you're not going to see as much. These you're going to see a lot. So there are, the other one would be CCl4, which is called carbon tetrachloride. We use this a lot, but this is actually the IUPAC name. Actually, it's not. This would be another one that, actually it's not. This would be another one that has a common name that we're going to use all the time. So let's put this into practice. Give reasonable names for the following molecules. Okay, so what I have to look at is my longest continuously connected chain, which is this guy. Now, I could do 1, 2, 3, 4, or I could do 1, 2, 3, 4. What I want to do is 1, 2, 3, 4. And why is that? Because that iodo in the bromo is a higher priority than a methyl. So that is going to want to have the lowest number. Notice I also have a stereo center here. So let's call this, I have a 2 bromo, I have a 2 iodo, and I have a 3 methyl. Those are my substituents. My parent is butane. So in alphabetical order, A, B, I'm going to have 2 bromo, C, D, E, F, G, H, I, 2 iodo, 3 methyl. Didn't leave myself enough room. And then that is going to be my stereo center. If I look at sort of flipping this up and looking at it, this is sort of pointing down. This is 1, this is 2, this is 3, and I'm going counterclockwise. So that would be the S. My methyl group is lowest priority, so I'm just going to flip it up. And yes, that would be S. All right, so here I'm going to do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I am going to either have a methyl, an isopropyl, and 2 chloros in either way, because that isopropyl is equivalent. So I'm going to number to give the chloro the lowest number. So what I have is a 5 methyl. I have a 4, I'm going to use the common isopropyl. And then I have a 2,3 dichloro. This and this are both stereo centers, but the hydrogen is pointing behind, which is lowest priority. So let's put this together. It's going to be a hexane derivative. It's going to be iso, right? So I'm going to have 2,3 dichloro. The C is the lowest. 4 isopropyl, 5 methyl hexane. And then on the 2 carbon and the 3 carbon, I have stereochemistry. So this is 1, 2, 3 in terms of priority. That's going to be R. And then this is 1, 2, 3. That's also R. So I have 2R, 3R. Dash, there's a dash there. 2, 3, 4-dichloro-4-isopropyl-5-methyl-hexane. Now, just a little bit about the structure of these alkyl halides. This is sp3 hybridized, so it's going to be a tetrahedral carbon. And I can use this primary, secondary, and tertiary nomenclature. So if the carbon that bears the halogen only has one other carbon group, it's going to be a primary. This is a primary chloride because it's Cl. If the carbon that bears the halogen has two carbon groups, it's going to be secondary bromide. And if the carbon that bears the halogen has got three carbons, it's going to be a tertiary because that's an iodine, it's going to be an iodide. So this is critical that you understand this. If something is primary, secondary, or tertiary, right, when I substitute, I am reacting at the carbon that bears the halogen. So we have to pay attention to how many carbon groups I have because of steric considerations, because of crowding. The more substituted carbon that bears the halogen will have difficulty undergoing a one-step sort of substitution. And we'll come back to that later. But just make sure you have to know the difference between primary, secondary, and tertiary halides because that's going to factor greatly into the type of chemistry and the mechanism that I choose when I start looking at the substitution and the beta elimination reactions. There's another sort of nomenclature that I use to designate carbons, and that's with this Greek letter. So Greek letters are often used to label the carbons of the alkyl group which is attached to the halide. So the carbon that's directly attached is called the alpha carbon, right? Substitutions will occur at the alpha carbon. So it's the bromine that's going to be substituted with other groups. Now, the next carbon encountered is going to be the beta carbon. So that's sort of 1, 2, right? The beta carbon is actually going to be sort of that second carbon away from the attachment. Remember, I undergo beta elimination. So it's one of the hydrogens that's on this beta position that actually is going to, we're going to get rid of. We did a little bit of this without calling it beta by looking at what alkene did I use to make the hydrohalogenation reaction occur and form the bromide or the alcohol or whatever. So we sort of did this a little bit in reverse in the previous chapter, which was chapter 5, but it's a beta hydrogen that actually eliminates. So this would be minus HBr, right? So it's the reverse of hydrobromination. So we're a little bit familiar with this, hopefully. And you have to become aware, or you will become aware, that the amount of branching at that alpha carbon affects the type of reaction mechanism that the substrate, which is the alkyl halide, occurs. So that's going to become very relevant later, that you know not only if it's primary, secondary, or tertiary, but also how to identify the alpha, the beta. The third array is called gamma. We're going to look at the hydrogens that are attached to the beta carbon in terms of this beta elimination reaction that we're going to study. So again, you have to be able to identify these different types of nomenclature and how I describe these different types of carbons in my alkane, my alkyl group. Okay, that's it for this lecture. I will be back shortly in order to continue. What we're going to continue with is going to be the going into the actual substitution and elimination reactions and reaction mechanism. So I will be back.